So far, we have learned scalar quantization and uniform quantization. We have mentioned that when we quantize a signal, the quantized value will tell you in which region your signal was. So you will have some errors within that region. And then we need to measure these errors. Sometimes this error is negligible, sometimes not. So one important measure that is used in all signal conversions, analog to digital or the other way around, is signal to quantization noise ratio. So in this video, we will discuss the concept of quantization noise and go through the basic steps of calculating the signal to quantization noise ratio, or SQNR. So the basic definition is that the input is a random variable with probability density function, and the quantized value is just a function of random variable x. In your probability course, you learn how to find a probability, because this is within a finite alphabet, how to find the probability mass function of q of x. So the signal quantization noise ratio is defined by the ratio of the power of the signal to the power of the noise, or the power of the distortion. The noise is exactly x minus q of x, which is the difference. This is defined the noise. This is a quantization noise. So the power of a signal divided by the power of noise is called signal to noise ratio, or SQNR. So if this number is very large, that means that the power of noise is negligible compared to power of the signal. But if it is not large enough, then you will have trouble. So expected value of x to the power of 2 is basically equal to integral of x to the power of 2 of x of x, and similar expression you can write for the expected value of the denominator. So when we are dealing with signals xt, we can neglect the time t, or write the power of the random process. So it's going to be, instead of these, is the same concept, same integral, and it's the same thing. Some people, they prefer to write power, some people, they prefer to write expected value to the power of 2. So the power of x of t is just another averaging over time, because this is time, and this is another averaging over time. It's not a big deal. So what we said is that for a quantizer, for a uniform quantizer, what we do is that we have time, and then we divide it into intervals. So let's say this is ai plus 1, and this is ai, and this distance is delta. If we want to calculate the distortion, we have to, or the denominator of SQNR, we have to calculate this integral. Because these quantized value in different intervals in this curve, there are different values. I break this integral. Instead of from minus infinity to infinity, I write it one integral from minus infinity to a1. Then I say plus integral from a1 to a2, then plus another integral from a2 to a3, and plus etc. And then I will have integral plus from an minus 1 to plus infinity. Okay, and whatever I put here is the same. So what I have done is that integral from minus infinity to a1, and then x minus the value of q of x. In the first interval, the value of q of x is a1 minus delta over 2, and so on. Because if this is a1, then you assume that this is a1 minus delta over 2, this is a1 plus delta over 2, and so on. Is the midpoint. And then you add this integral, so you get this summation, and this is the integral for the last one. So you have one integral for first one, because it starts from minus infinity to this one integral from the last one, which is, let's say the last point is a1 plus n minus 2 times delta. Okay, so from this point to infinity is for the last integral, but all of them is sum of those integrals. If you want to optimize or calculate these integrals, is tedious, but you can do it. You know the math, you know the calculus, but this is a tedious optimization problem. So this is for the general case. So for non-uniform quantization, the only difference is that these intervals are not equal to delta, so you will have integral from minus infinity to a1. So you divide your line, so this is, let's say, input. So this is a1, a2, and let's say you have an minus 1. So you say that this integral divides from minus infinity to a1 plus from a1 to a2 plus a2 to a3, etc., which is giving you this sum, and from an minus 1 to plus infinity. So you have to calculate this integral. Now we want to minimize the distortion. So suppose that I want to design the value of a1, a2, an. I want to minimize, the objective is to minimize the distortion by tuning and choosing the values of a1, a2, etc. So I could calculate the derivative of the distortion, the derivative of this expression, with respect to ai. Moreover, the quantized values that they appear in these integrals, I could also minimize the distortion with respect to x hat 1, x hat 2, etc. So I could calculate not only the derivative of the distortion with respect to the boundary of my regions, so this is the boundary of my regions, but also with respect to the quantized values. So if you do that and set it equal to 0 with some math, you will find that ai is equal to the midpoint of the two successive quantized values. So the border, the boundary of the regions, if you know the quantized value, regardless of your PDF, regardless of the distribution of the input, and regardless of anything else, is just the midpoint of that. So if you have already calculated x hat 1 and x hat 2, a1 is just the average of the two. And now, if you calculate the derivative with respect to ai and calculate, you could say that the quantized value in each region is basically given by this integral. And this integral is nothing more than the conditional expected value of x, given that x is in that region. Now, this may seem to have a closed form expression, but it is not. Because in order to calculate ai's, so you need to calculate a1 to an, and you need to calculate x hat 1 to x hat n. In order to calculate this set of values, you need this one, and in order to calculate this one, you need the set of these values. There are iterative methods that they guess some of these values, they calculate the other one, feed it back, and then iteratively they calculate this one back and forth and so on. And then hopefully they converge, and then for a given distribution, they give you the optimal quantizer. So designing the optimal quantizer is possible using these two set of equation. Or alternatively, for a given distribution, you can try to solve the set of equation, because remember that x hat I is a function of these boundaries, and these boundaries are a function of these x hat I. So they are linked together.